Hello and welcome. What is the best state to buy school supplies? Pennsylvania. In Packet 1, we learned how to find limits visually by looking at graphs. But what if we don't know the graph of a function? How can we find its limit? In this video, we're going to take another look at limits, this time numerically and algebraically. You might say we're going to push your algebra skills to the limit. But enough puns. Let's sharpen our pencils and get to the point. First, we'll take a numerical approach. That is, we'll plug in numbers to find limits. Example 1 says, find the limit as x approaches 3 from the right of x plus 2 over x minus 3. And what I've done here in the table is create a row that shows x values that are getting closer and closer to 3 from the right. So these would be x values like 3.2, 3.1, 3.01, and so on, getting closer and closer to 3, but from the right side of 3. Right, if you drew a number line, it would look something like this. Here we're approaching 3 from the right. So 3.2, 3.1, 3.01, those are numbers getting closer and closer to 3, but from the right side of 3. And the next row is just looking at x plus 2, just that top part of the fraction, x plus 2. So we're breaking apart what is happening to the top numbers, and then what's happening to the bottom numbers, those x minus 3s, what are those evaluating to when we plug in these different x values? And then the last row is overall, what is x plus 2 over x minus 3? So we're trying to break this down into detail, one step at a time. So these are the x values that we're plugging in that are getting closer and closer to 3. Here's what the top numbers are going to evaluate to. In other words, what x plus 2 will evaluate to. Well, that's just going to be 3.2 plus 2, which is 5.2. 3.1 plus 2, which is 5.1. I mean, all we're doing is adding 2 to all these x values. And so what does it look like the x plus 2, in other words, the top of the fraction, is getting closer and closer to as the x values get closer to 3? What are the top numbers getting closer to? If you said 5, that would be correct. Here you can see 5.0001. If x gets closer to 3, then x plus 2 will get closer to 5. So the top numbers are approaching 5. What about the bottom numbers, the x minus 3s? What are those numbers approaching? If you said 0, that's correct. And not even just 0, but we're going to come away with more than just 0. We're going to say that the bottom numbers are approaching 0, but they're approaching 0 and are positive. So POS standing for positive, not point of service. Or point of sale, I think is the way. Anyway, this is going to be an important distinction because if we were approaching 0 but from the negative side, which can happen, all these numbers could be negative and we'd still be approaching 0, but we would be approaching from the negative side, that can have an influence on the sign of the overall expression of the overall fraction. So we're getting close to 0 on the bottom, but we're also staying positive the entire trip, the entire journey we're staying positive. And then here we have x plus 2 over x minus 3. This is really what our goal is. That's what our function is. To get these values, all we have to do is take the top values, which are this row, so the x plus 2 row, divided by the bottom values, which are x minus 3. So if you took, for example, 5.2 divided by 0.2, you would get 26. If you took 5.1 divided by 0.1, you would get 51. That kind of makes sense because 0.1 is 1/10, and if you divide by a tenth, that's like multiplying by 10 over 1, so 5.1 times 10 is 51. That you can do kind of in your head there. And these ones are actually pretty similar because 0.01 is like 1 over 100, so really you're just doing times 100 to the 5.01 to get 501. But the main thing is you get these numbers that are doing something. What does it look like, these numbers overall for the x plus 2 over x minus 3? What are they doing? They're approaching infinity. So if you said they're getting larger and larger or approaching infinity, that would be correct. We're going to say arrow infinity. These are approaching infinity or going to infinity. So that's what our analysis is. This limit that we just evaluated by doing this numerical analysis is infinity. We could even box that. Looking at example 2, we're asked to find the limit as x approaches 2 from the left of 5 minus x over x minus 2. And once again, I'll just draw a quick picture of 2 and show that when we have x approaches 2 from the left, remember that this means the left side of 2, but getting closer to 2. So this is this kind of motion. So we're picking out values that are smaller than 2, like 1.8, 1.9, 1.99, 1.999, 1.999. I think I said too many nines there. But the point is that these numbers are going to be getting closer and closer to 2 from the left. So these are just some sample x values. It doesn't have to be these values, just some sample x values getting closer to 2 from the left. Then we plug in those x values. Again, we're going to break it up into the top of the fraction and the bottom of the fraction. So plug them into the top, see what we get. Plug them into the bottom, see what we get. And then we'll have some numbers to then divide and see what happens overall to the fraction. What is this fraction evaluating to? It's like we're doing PEMDAS, really. We're just following the order of operations. We do what's in here, then we do what's in here, and then the last thing we do is divide. So 5 minus x, if we take 5 minus 1.8, we get 3.2. 5 minus 1.9, we get 3.1. What does it look like the 5 minus x's are approaching? Yeah, if you said 3, that would be correct. What about the x minus 2's? What does it look like those are approaching? If you said 0, that'd be correct. And then not just 0, but what else are we going to put here? Negative. They're getting close to 0, but they're negative. That's going to be an important part of our analysis when we move away from these tables of numbers and try to conceptually think about what these numbers are doing and how they're behaving. So now when we take 3.2 divided by negative 0.2, we would get negative 16. 3.1 divided by negative 0.1, and we'll get negative 31. Notice how all of these numbers that we're getting on the bottom row, which are the numbers that we're interested in, all of these are negative because the top numbers are all positive, the bottom numbers are all negative, and a positive divided by a negative is going to be a negative number. So these overall numbers are going to be negative because the top is positive, the bottom is negative. And so what are the overall 5 minus x over x minus 2's approaching? Negative infinity. Yep, negative infinity. They're getting bigger in an absolute value sense, but they're negative. They're all negative. So negative and then negative sort of big numbers, so negative infinity. Okay, now we could look at this and just say, all right, the top is positive, the bottom is negative, so we know that these numbers overall are approaching a negative number. And then to get the infinity part of it, we just have to realize that the top is approaching a non-zero number. That's important. And the bottom is shrinking down to 0. When you shrink the bottom down to 0, dividing by that bottom number that's really close to 0 makes the fraction bigger. Like dividing by 1/100th is the same thing as multiplying by 100, which makes the number bigger. Dividing by 1,000th, even negative 1,000th like we have here, is the same thing as multiplying by 1,000 or negative 1,000, which makes the number bigger in the absolute value sense. So the bottom shrinking down to 0 is what's causing these overall fractions to blow up to some kind of infinity, either positive or negative, depending on what the signs of the top and bottom are. So this is an important intuition to take away from these tables of numbers. We're not going to be spending time making these tables of numbers. We're going to be more thinking about the concepts and what happens when the numbers behave as they do. Looking at example 3, we have the limit as x approaches negative 4 from the left of that fraction, 1 minus 2x over x plus 4. So here's negative 4. If we're approaching negative 4, from the left, looks like that. So left side, but we're getting closer to negative 4. So these are numbers that are a little smaller than negative 4, like negative 4.2, negative 4.1, negative 4.01, and so on. Those are numbers that are smaller than -4. Plug those numbers into 1 minus 2x, that top part of the fraction, and we've got numbers that are approaching what? 9. My voice fell kind of flat there. Approaching what? All right. So then what about the bottom numbers, x plus 4? The bottom numbers are approaching 0 and are negative. Now overall, when we divide these, we're going to get negative numbers because the top, again, is positive and the bottom is negative. So overall, that's going to give you a negative number. And these negative numbers keep blowing up, getting bigger and bigger in the absolute value sense. And so the overall numbers are approaching negative infinity. And just remembered I forgot to write negative infinity up here and box it in celebration. Let's now transition away from these tables of numbers into a more analytical way of thinking about it. So in example 4, we're asked to find the limit as x approaches 3 from the left of another fraction. So we have a rational function, which is a polynomial over a polynomial. It's like a fraction of polynomials. And what we're going to do is, rather than make a table of numbers, analyze what's happening to the top of the fraction and the bottom of the fraction separately, and then think about what happens when we combine those two effects together. So as x approaches 3 from the left, what is 2x plus 1 approaching? Without plugging in all those tables of numbers, what do you think the bottom or the top is approaching? If you said 7, that would be correct. And if you're not sure how to get that 7, what you can do is just think, if x is getting closer and closer to 3, then 2x plus 1 is getting closer and closer to the number that you get close to when you plug 3 in. So basically, to figure out what 2x is getting closer to, you can plug in the destination x value, which is 3. So you do like 2 times 3 plus 1, which equals 7. So 7 is what those top numbers are going to get close to. As x is getting closer to 3, the 2x plus 1 calculations are going to get closer to 2 times 3 plus 1, which is 7. So the top is approaching 7. And then the bottom numbers, what are the bottom numbers approaching? If you said 0, that would be correct. Once again, you can take the 3, plug it in, and you'll get 3 minus 3, which is 0. So the bottom numbers are approaching 0 as x approaches 3. Now you might wonder, like, why don't we just plug in x equals 3 into this whole fraction right here? Well, the problem happens because the bottom is approaching 0. And if we just tried to plug in x equals 3, we would just get 7 over 0, but that's undefined. And undefined is something that really is associated with plugging in specific values into functions. But with limits, we're thinking more about what is happening as we get close to x equals 3, not what's happening at x equals 3. At x equals 3, this function is undefined. But as we get close to x equals 3, what we're asking with this limit is, what's the behavior of this function? What is it doing? Is it getting close to a specific number? Is it blowing up to positive infinity? Is it going down to negative infinity? What's going on? But that didn't stop us from plugging in numbers separately into the top and the bottom to figure out what the top and the bottom are getting closer to. It's just that when we put everything together, we can't just do 7 divided by 0 because we're never really at x equals 3. We're just close to x equals 3. Now, one more piece of information that we're going to want is what the sign of the bottom is as we get close to 0. And here it might help to draw a picture of 3 and remind ourselves that we're approaching 3 from the left. So we're approaching 3 from the left. So when we think about numbers that are close to 3 from the left, maybe I'll here, do this, yep. So numbers that are getting closer and closer to 3 from the left, these could be numbers like, I don't know, 2.9, 2.99, and so on. I drew way more tick marks than there are numbers up there, but so these are numbers that are a little smaller than 3. Now if you take those numbers that are a little smaller than 3 and you plug them into x minus 3, what is the sign of x minus 3 going to be? If you said negative, that would be correct. So no matter which number you plug in that's smaller than 3, that's on the left side of 3, x minus 3 is going to be negative. And especially as you get close to 3. Now, the thing is, here it actually doesn't matter which number you plug in less than 3, but sometimes when you have more stuff going on the bottom of the fraction, and you plug in x values like negative 1,000,000, that could affect the sign of other factors that you might have on the bottom. So, which is not really the idea here. The idea is that we're getting close to 3. So you want to get these numbers pretty close to 3, and that's why I'm picking these decimals like 2.9, 2.99, just to make sure that these numbers are close to 3 and that they're not going to cause any of the other factors on the bottom to be a different sign. We'll see that issue come up in some future examples. So now the top is approaching positive 7, the bottom is approaching 0, but it's negative the whole way. So what's the sign of the overall, what are the sign of these numbers going to be? If you said negative, that would be correct. And then what is it that these are approaching then altogether? That's right, negative infinity. Negative infinity. Because the bottom's shrinking down to 0, and that causes these fractions to become bigger and bigger. The smaller the denominator, the bigger the overall fraction. Another way of thinking about it is you can write 1 over a small number is going to be a very big number. Even if it's 7 over a small number, a smaller and smaller number, those are going to be bigger and bigger numbers. That's a way you can think about fractions. So for example 5, we have the limit as x approaches negative 1 from the right. Another fraction, so 2 plus 3x over x plus 1. What are the top numbers approaching? By the way, bot just stands for bottom. So what are the top numbers approaching? If you said negative 1, that would be correct. Once again, you can plug in your destination of negative 1, and you'll get 2 plus 3 times negative 1, which is 2 plus negative 3, which is negative 1. What about the bottom numbers? Approaching 0, that's right. Now we're approaching, now the x values are approaching negative 1 from the right side. There's the right side of negative 1, and we're getting closer to negative 1. So when we're thinking about whether or not the bottom is a positive number or a negative number, we can think about what these values are that are getting close to negative 1 from the right. So these would be numbers like negative 0.9, negative 0.99, things like that. If we plug those in to x plus 1, is that going to be a positive number or a negative number? If you said positive, that would be correct. Like you can take one of those, negative 0.9, for example, plus 1. That's going to be positive 0.1. There's more positive than there is negative here. So overall, what is this going to tell you that the limit is equal to? If you said negative infinity, that would be correct. Negative because you have a negative divided by a positive, which gives you the negative. Infinity because the top is going to a non-zero number and the bottom is shrinking down to 0, causing the fraction to blow up to infinity. And then it just happens to be signed negative, as we mentioned. Example 6 says find the limit as x approaches 2 from the left of the same fraction. So here we can think about what the top and the bottom are approaching again. So it's the same fraction, it's just that now we're approaching, x is approaching 2 from the left. All right, so what's the top approaching when x approaches 2 from the left? If you said 8, that would be correct. Again, plug in 2 to figure that out. You take 2 plus 3 times 2, and you get 8. What is the bottom approaching? That's right, it'd be 3. 2 plus 1 gives you the 3. Now, here, what would the overall fraction be approaching then? It would be 8/3. 8/3. Here, we don't have any of the issues that surround division by 0. Like the issue here was that the bottom was approaching 0, so something was happening to this overall fraction. But here, the bottom is not approaching 0, it's just approaching 3. So if the top's approaching 8, the bottom's approaching 3, well then overall the fraction is getting closer and closer to 8/3. So that's what the limit is, just 8/3. It's just that number. Nothing special about that particular limit. No offense, example 6. All right, let's look at example 7. Here we have the limit as x approaches pi/2 from the left. Now this looks a little bit like funny notation, but the parentheses are there just so that you know where this negative superscript is what it's doing there. It's above this whole pi/2. So it's x approaching pi/2 from the left of e to the secant x. E to the secant x. All right. Now, here it's going to help. So when we're plugging in the x values, we're plugging them into the secant first. That's the important thing. We're plugging them first into the secant. So it's going to help to have a picture of the graph of secant. Here's where graphs are going to help us out. Don't really have to write the x and y. But we're going to draw just one period of secant to help us out. Remember that secant is 1 over cosine. So if you think about the graph of cosine, you can draw the graph of cosine and then invert it to get secant. So you take the graph of cosine and then 1 over cosine's values is going to invert that whole graph and give you secant. So it looks something like this, where cosine is 0, which is like at pi/2, you have a vertical asymptote. And then actually there's another one here at 3 pi/2. There's another vertical asymptote. So then they're going to meet at 1 and -1. Let's draw a quick secant. So it kind of goes up like this. Where cosine goes down, secant is going up. And then here, where cosine goes from pi/2 to 3 pi/2, kind of goes below the x-axis, inverting that brings it down. So here's the graph of secant. Actually, it goes on, there's more of it like right here. And of course, it's periodic, so it goes on infinitely in both directions. This is just a quick picture of what secant x might look like. Now, in our case, the x value that we're approaching is pi/2, and we're approaching it from the left. So we're coming into pi/2 from the left. Now that means we're traveling along this part of the secant graph, which is blowing up to positive infinity. The outputs, or the y values of secant, are going up to positive infinity as the inputs are approaching pi/2 from the left. So if we think just the secant x numbers, those numbers are approaching infinity as x approaches pi/2 from the left. So just this part, those numbers are getting bigger and bigger and bigger. They're blowing up to infinity. So then those numbers are being plugged into the exponential function. So if we draw a quick picture of the exponential function, I'll just draw it over here. Here's the exponential e to the x. Now we don't have an e to the x, but think about here, this x is just, this is not the same as the other x right here that's going to pi/2. This x is just the standard old, let's look at it separately, e to the x, and think about the inputs and outputs. So this x is just representing a number that you're inputting into the exponential function. Now the inputs into this exponential function are the outputs of the secant x graph, which we know are going to infinity. And so the numbers that we're plugging into this exponential are numbers getting bigger and bigger going to infinity. So when we're looking at the e to the x graph, we're going to think, what happens when our inputs to this exponential function go to infinity? What are the outputs doing? And the outputs are going up to infinity. The y values, as the inputs, as the x values, or the inputs to exponential go to infinity, the y values, the outputs, are going up to positive infinity. So overall, this limit is positive infinity. And that's because of this part of the exponential graph. Okay, so the key thing was, another way of analyzing this is you can think secant x, this part of it, these numbers are approaching infinity. And then you have this other layer, which is those numbers going to infinity are being plugged into the exponential. So when you input those numbers going to infinity into the exponential, the outputs are going to positive infinity as well. That's a kind of looking at it and seeing what the parts are doing kind of thing. If we were to write it out in a table, we might have a row that says, what are the secant x values? And just calculate the secant x values as x approaches pi over 2 from the left. And then the last row would be, let's take e to those values, e to the secant x values. And you'll notice that those values are also going to positive infinity. Let's do some more examples that are similar, along the same vein. In example 8, we have find the limit as x approaches -2 from the right of ln of 4 minus x squared. Remember, this is the natural log function. It's the inverse of our exponential function base e. Now here we have this inner function, the 4 minus x squared, and we can just analyze what's happening to that. We can take that x value, plug it into 4 minus x squared, and figure out what's happening to that. Let's do that analysis here. Well, if we plug in -2 inside, so we would have 4 minus -2 squared, which is going to be 4 minus 4. Remember that -2 squared gives you +4, but we're subtracting that +4. So that gives you 0. So the 4 minus x squared is approaching 0. Now we can say even more than that, because every time we have something that's approaching 0, we want to ask ourselves, is it approaching 0 from the positive side or from the negative side? Because it's going to make a difference. Well, here we have to think, what are these x values? Are they what are these x values that are approaching -2 from the positive side? Let's draw a quick number line to think about these x values. So for the x values, I think what I'll do is choose a different color. So for these x values, they're approaching -2 from the positive side, from the right. So over here, it's like, you can think of it as -2 plus a little bit. So these numbers are numbers like 1.9, sorry, -1.9, -1.9, -1.99, those kind of numbers. Now if you take those numbers and you plug them into the 4 minus x squared, just that part of it, so take like 4 minus -1.9 squared, is that going to be positive or negative? That's right, it's going to be negative. Negative because when you input a number that would be like 2 or -2, like we saw, that's right where you get 4 minus x squared equal to 0. Anything bigger than 2, and now you're going to be subtracting more from 4, but anything smaller than 2, and you're subtracting less from 4. So if you plug in the -1.9, you're going to be doing 4 minus some number that's going to be smaller than 4, and so that's going to give you, that's going to give you a positive value. So if you said negative, you wouldn't quite be right, actually. Oh boy, okay. Just testing. Yeah, because here you have a smaller number that you're taking away, 4 minus this smaller number. All right. So then we can say that 4 minus x squared is approaching 0, but it's positive. Okay, now those numbers that are approaching 0 and are positive are being inputted into the natural log function. So let's draw the natural log function to get a sense of what happens to the outputs when the inputs of the natural log function are changed. So here's our natural log function. I'm just calling it natural log of x, just drawing a standard natural log function, even though we know we have something else in here. But here we're just saying natural log of x, where x over in this picture is like whatever is being inputted into the natural log function. And here's our 1. Well, it looks like our inputs into the natural log, which is what the 4 minus x squared is representing, those are getting inputted into the natural log. Those inputs are approaching 0 and are positive. So when we approach 0 from the positive side, we're making this kind of motion with our inputs. So we're getting closer to an input, or in our picture here, an x value of 0. And then the outputs we can track by following along the natural log curve. So what does it look like the outputs are doing? Yeah, they're falling down to negative infinity. So we could even write natural log of 4 minus x squared is approaching negative infinity. So that's what the outputs of natural log are doing, and those are then what the whole function is doing. All right. So our last one for the page, example 9. Find the limit as x approaches infinity of 2 over inverse tangent of x minus 10. Now here, if we look at the chain of what we're plugging in, we're plugging it first into the x minus 10. So we can figure out what is going on with x minus 10 first. Let's figure that out. Oops. Well, as x approaches infinity, x minus 10, what is that going to approach? Infinity still. If you subtract 10 from a bunch of numbers that are getting bigger and bigger and bigger, your numbers are still getting bigger and bigger and bigger towards infinity. A million minus 10, a billion minus 10, a trillion minus 10, those numbers are still going to be evaluating to numbers approaching infinity. Now those x minus 10 numbers that are approaching infinity are being plugged into inverse tangent. So now we have to figure out what is inverse tangent of x minus 10 approaching. Let's draw a picture of a standard inverse tangent graph. Remember, inverse tangent has 2 horizontal asymptotes. There's one at negative pi over 2 and one at pi over 2. Starts from left to right as you draw it. It starts close to the negative pi over 2 asymptote and then goes up to the pi over 2 horizontal asymptote. This is a quick sketch of inverse tangent. Now, if the inputs into this inverse tangent, the inputs are represented by x minus 10, and we just said that x minus 10 is approaching infinity. So if we wanted to circle this, we could write here the x minus 10s are approaching infinity. So those numbers are being plugged into the inverse tangent. So the inputs into inverse tangent are going to positive infinity. What are the outputs then doing? If you said they're approaching pi over 2, that would be correct. They're approaching pi over 2. So then those numbers that are approaching pi over 2 are then being taken, or you take 2 and you divide by those numbers. So couldn't finish that sentence. So when you take 2 and you divide by those numbers, those inverse tangent numbers that are getting close to pi over 2, you get numbers that are approaching 2 over pi over 2. Which would be, if you divide by pi over 2, that's like multiplying by the reciprocal. So you get 4 over pi. So the overall fraction 2 over inverse tangent x minus 10 is approaching 4 over pi. So there we can write that this limit is 4 over pi. Just to finish up what we talked about over here in example 7. So here we could take this inverse tangent, we could circle it and say those are going to pi over 2. And from here, it's just a matter of evaluating these numbers. 2 divided by pi over 2, that's 4 over pi. Make sure to box that. Also, to close the loop on example 8, we first figured out what was happening to the 4 minus x squared. That was approaching 0, and those things were positive. And then we plugged those numbers into natural log and figured out that the outputs in that case were approaching negative infinity. Squeezing that in there. Okay, well, this is a pretty good place to stop for this part. Thanks for watching, and see you in the next part.